Hello everyone. My name is Prabhat Kumar, and today I will try to derive some basic differential governing equations for bar element having load in axial direction, uniform variable load in axial direction. So we'll start. So let's suppose we have a bar element like this. This is our bar element, and what we are saying is this load is basically from increasing from this side to this side, and this, let's suppose we are taking a small section here. It is of dx length, and if we are assuming this length to be x, from here total length we are saying as to be L. Okay, and this axially distributed load I am saying is q into x. For example, uh, if you are saying how much load on this small strip, means how much load on the strip, so it is basically q into x. Okay, and its unit is, so it will be q into x times dx. Okay, so this is the load acting on this particular strip. Basically it is not acting, it is on this strip. Okay, now if we select another strip, let's suppose its location is dx2. Let's suppose this is dx2 and it is x2 distance from this end, o end. Okay, for this the load acting on dx2 will be how much on dx2? It will be how much? It will be basically qx2 dx2. Okay, so in this way this much of the load is acting on each strip. Okay, so if I am saying how much total load is acting, if we are, let's suppose we have this section. Okay, this I am considering is a dx section, that small section. So how much load we will consider? Basically this will be right side of over that beam, and this, so it will be, okay, wait, it will be like this strip, this strip, this strip, this strip. So basically the total load will, like, you can assume like this way. Suppose this is chain and all. Okay, so here if we consider weight on this, weight own weight, it will be its own weight. For this, if we consider its weight plus its weight, in the same way if we consider what will be the weight acting for this particular circle, it will be the summation of loads on each of these elements. Okay, plus some on it also. So in this way, if we have to calculate how much total load acting on this dx, so it will be basically, how much? It will be q times x into dx, and it will be basically summation for dx1 dx2 dx2 till end. So we will do a integration from x to L. Okay, so this will be the total load acting on dx. Total load acting on dx. Now if we'll solve this, how much value will get? So q will be constant, it will be x square divided by 2, lower limit x, upper limit will be L. So from here we will get q times L square divided by 2. Basically we can write directly like this, q by 2, and it will be L square minus x square. Okay, so for this strip at dx, at x length, that dx strip, total load, how much it is acting in axial direction, it will be q by 2 L square minus x square. Okay, this is the total load. Total load. Now Now if we this will be our total load, and if we say, let's say the cross sectional area in this particular section will be, if we say cross section area will be A, so what will be the stress here? The stress here will be, total load acting divided by area. Okay, so how much this equation term we will get from here? So we'll get basically it will be q by 2 L square minus x square divided by A. Okay, this will be our stress value. Got it? Now if we consider this the whole system, let's just copying it and I will putting it here. So yes, I'm just trying to remove this section. Yeah, so if we see this section, that dx1, this is ds section, this is dx. Let's suppose here our displacement is u1 and here our displacement is u2. So if we calculate strain, so how, like, we can write strain small e, we can write as u2 minus u1 divided by del x. Okay, or we can write it as du by dx. This is our strain for one dimensional this bar element. Okay, this is particularly for this bar element. Now we all know that I'm assuming this as an isotropic material, so we know that we can relate stress with strain as sigma e times small e strain. So put the values. So what we will get? We have sigma. How much we have? Q by 2. So it is Q by 2 L square minus x square divided by A equals to E into, we can write it at du by dx. Okay, now just rearrange this equation. So we will get like EA del u by del x equals to q by 2 L square minus x square. Okay, so we can do one thing, we can differentiate it once with respect to x. What we'll get, since area is constant, E is also constant, I can write it as del u2 by del x2, and here I will get q by 2 and it will be minus 2x. Okay, it will be minus 2x. Now what we are getting here, this 2 will be cancelled with this value and we will get a equation like EA del 2u by del x2 plus q times x equals to 0. So this equation that we got here is basically governing differential equation for the bar element having a uniform variable load in axial direction. So if we say what is the unit of this whole term, this is basically Newton per meter. Okay, this is the Newton per meter. Suppose it is acting for dx section, it will be net force acting on dx section, basically on dx, basically it will be qx times dx. Okay, so this we got differential equation for governing differential equation for bar element. Okay, fine. Okay, that's it for the differentiation, like derivation for this governing differential equation. And in the further lectures we will see how we can convert this into weak form, and then we will do the formulation for FEA. Okay, so see you guys in the next lecture. Bye.